Hello and welcome back to the Hyperthesis episode 63. Today, again, we have special guest Troy Allen to join us and to talk about some physics and engineering and lasers. Welcome, Troy.
Thank you. Happy to be here.
My name is Pheely.
I'm Patrick.
And I'm Liam.
And I'm Troy.
All right, so we are back. 63. Just December rolls around, so starting snowing. Everything's starting to get a little colder, a little more moist, which is kind of nice sometimes. But anyways, today we have I think we don't have that many engineering type coming along for our podcast, so it'd be great to hear from you. But before we get to the main topic, which is Troy, we're gonna start with some intro topic. I think Liam prepared something on some laser thing that he heard of.
Yes, but Pheely, can you tell us a little bit about Troy first, so that we have or can Troy tell us? Pheely, you should have had something prepared. I will judge you if you didn't prepare anything.
Yeah, so Troy just defended his PhD. So it'll be very soon future Dr. Troy Allen. So Troy worked in Fraser's lab, Fraser's group here at Queen's University, and he's been at Queen's for quite some time. So he's his master's here also, but he also had a background in engineering, and he moved into physics in PhD. So his work is on laser in additive manufacturing, something that work in factories, for example, in manufacturing something like laser welding technology, and working on to not exactly when you think of engineers, like, work on the line or figure that part out, but his work is more fundamental. We're working on mechanism, how to basically fit the laser into the system and how it works, how should the laser work. Hopefully I get something right, but we'll hear from him in exactly what he does. So,
all right, so awesome. So therefore, my intro topic is on lasers. So hopefully, Troy, you're the expert here.
Okay.
I know a little bit about lasers, but I definitely do not focus my research on them. So, our friend and previous guest Dean Eaton sent a paper our way titled Laser Pulse Compression by a Density Gradient Plasma for Exawatt to Zettawatt Lasers, which was published in November this year in Nature Photonics journal. So this paper, the scientists who published it from the UK and South Korea are proposing basically a new method of creating ultra-powerful laser pulses. So currently, the most powerful lasers humanity can create, they're about 10 petawatts, according to this paper and this article I found that was with the paper. For some context, some varying degrees of context, 1 petawatt is 10 to the power of 5 watts. 1 horsepower is about 750 watts for the car and horse people out there. Patrick?
10 to the power of 15 watts, not just 5.
Did I say? I thought I said 15.
I heard 5.
Oh, okay. Sorry, I misspoke. 10 to the power of 15 watts. Yes, 1 petawatt is 10 to the power of 15 watts, not 10 to the power of 5. My bad. Another kind of example of power is the Niagara Falls hydroelectricity plants in Ontario/New York. They generate about 4.9 times 10 to the power of 9 watts of power. So 1 petawatt is way more than that. Just for some context, and the sun produces about 400,000 zettawatts, where a zettawatt is about 10 to the power of, 10 to the power of 26 watts. Did I get that right? I think I did. I'm doubting my notes now, but anyway, it's a lot of power. So a laser being able to produce 10 to the power of 15 watts is already pretty impressive. That's already a good amount of power. Even though these high intensity lasers are often over very small timescales. It's not like they're producing this high intensity light for a long time. They're usually very short timescales. Still impressive though, so it's very interesting that people are proposing that you can do even more. The standard way people produce these high intensity laser pulses is called chirped pulse amplification, which is something Dean knows a lot about. He's the one who sent this paper our way, and he knows a lot about it because his supervisor won a Nobel Prize for it, which we talked about before. However, there's a limitation with this chirp pulse amplification, which I won't get into. So by being able to produce laser pulses beyond this limit, you could do a lot of things. There's a bunch of different applications for it. One of them being that you can probe fundamental physics. So as a theorist, that's the one I think of the most. I'm sure there's more useful real world applications, but once you reach these higher intensities up to zeta watts, the order of magnitude that the sun can produce, you can actually begin asking fundamental questions about the nature of reality and quantum field theory and quantum gravity, which is something that we really struggle to deal with. So what does this paper actually talk about? I've just talked about what it could end up teaching us about. The paper, they used computer simulations, the researchers, to demonstrate that light can be compressed and increased even more by using this interesting type of plasma mirror. So this plasma mirror, imagine that you're firing light into a plasma. Plasma is a bunch of ionized particles, and it scatters backwards. It kind of reflects off of it. It turns out that if you have this gradient in density of the plasma, so as you go deeper into the plasma, it gets denser and denser. The light going in, if you shine in white light, it reflects out different color, different wavelengths that make up this white light reflect out differently. So you can imagine like a prism, like, the Pink Floyd or the Pink Floyd cover photo they use all the time. It's a prism, you shine white light in, and it gets kind of separated into these different colors of the rainbow. What happens here is that you fire in this high intensity laser pulse consisting of all these different colors, and so certain ones reflect differently. Red reflects differently than blue, it reflects differently than green, and so on. And as they reflect out, they kind of recombine into a really tight, high intensity pulse.
Wait, you mean refract or reflect?
Reflect, yes.
Okay.
Isn't it refraction?
Well, for a prism, when you shine light through it, that's refraction. But sorry, maybe that was a bad example.
Well, I thought because the gradient in density is like when you explain an analog black hole, but imagine a gradient in speed, right? It's like, so it's
Yeah.
the outer wavelength need to catch up, so it intensify the amplitude.
In the paper, they have this diagram of the light reflecting out, not just traveling through, and yeah, they do.
No, because it's refracting, but it's making a full 180.
Yeah, that's called a reflection.
Yeah, but it's not actually, I guess, in this case, bouncing off a surface. It's being
more like
refracted consistently until it...
Yeah, absorption and
okay,
re-emission.
okay.
Is that what's the accurate? Well, I think we discussed about this before. What is the mechanism of refraction? Is it absorption and re-emission, or is it some kind of just changing the trajectory of the light?
Okay, I guess the simple way to put this is that you fire light in a pulse of high intensity light consisting of all these different colors. So it's like a white light pulse. It goes into this plasma, it does a bunch of stuff, and when it comes out, the colors have kind of came out differently, such that when they recombine, they're even tighter together and make a way more intense pulse of light.
So just talking about this in terms of refraction, because I think this plasma with a density gradient is, the key factor of this. And thinking about this in terms of refraction, if you look at, for example, the Pink Floyd poster, where you have this white light going in and then these colors going out, it's kind of working in the reverse direction. So you have different colors going in, and because each wavelength of light that produces these colors is being refracted differently, very slightly, but enough that it creates a noticeable effect. when you have this this gradient of density, these wavelengths of light are behaving the same, so they go in all separately, and then they essentially make a U-turn, and that's very dependent on how the gradient is composed, which is a whole experimental side, which I'm sure they touched on in the paper, but I just read kind of briefly through it. And essentially it takes all those separate colors together, and then they all exit that gradient essentially at the same time.
Yeah. Okay. The way I'm thinking of it is, yeah, exactly. It's like this. It's like a focusing mirror made out of plasma in some sense. It takes all these different wavelengths of light. They kind of go in, they do whatever they do, and they bounce out focused such that you get a higher intensity. So the current intensity I said that we can get is this 10 to the power of 15 watts. So this method, according to their simulations, you might be able to get 10 to the power of 18 to 10 to the power of 24 watts if all goes well. I'm sure experimentally it's way more difficult than it was very difficult to achieve, but it seems like they can do it. They seem pretty confident.
Yeah, this is really interesting, and I wanted to clarify. It sounds like this, your friends in the paper, are they a student of Donna Strickland?
So they're not, yeah, they didn't do the paper, but they like sent it to us
Right,
and said
okay.
they saw, yeah, exactly. They work for
'Cause
Donna Strickland.
That makes sense.
Yeah.
As soon
So
as I
they-
heard what the topic was, I'm like, well, that sounds like, the Nobel Prize. So is this new technique, are they already sending in a compressed pulse that they've already compressed using the best method they can, and this just compresses it further?
That was my understanding, is that that's something I don't understand, because I had the original picture that they're sending in like a compressed pulse, but it's consisting of different colors of light. So it's effectively like a white pulse of light.
But okay, so
But I don't know if that.
Yeah.
And then Patrick was saying that they sent them in separately, so I'm not quite sure exactly what happens.
So any pulse that's very short in time is very broad in frequency and broad in wavelength, and that's sort of how chirped pulses work. Is that they chirp out a pulse, and I'm not expert on this. Your friend would know better, but you chirp out the pulse through like a long fiber, for example, so that it's now all the wavelengths are now arriving at very different times, and then using some technique, you later recombine them to as close to a single moment as you can, so that all of that power comes out at one time. So my guess is, like you said, that this effect is focusing, and I don't think it's not focusing in the sense of a lens. I think it's focusing in time. I think.
Yeah, I guess that's a way better way to put it than I did. Yeah, you have your energy time uncertainty relation. Makes sense. So that is what it's doing. It's making this pulse really, really, really short in time scale. So I guess normally you have like femtosecond. High intensity laser pulses are femtoseconds. I didn't actually see a time scale in this. I didn't fully read the paper. I kind of like skimmed through it a bit. So Patrick, I don't know if you know the time scales that these. I guess they're way higher energy, so their time scales have to be even smaller than femtoseconds for sure.
I am just looking at the paper right now, and it is an input of a frequency chirp pulse laser, which in the case of this paper they refer to as a long laser pulse, because like you said, it compresses it in time, and that's a really good way to put that. Is it compresses this chirp pulse even more in time, so it's a much higher peak power. But again, it lasts for a lot less time. I'm just looking through the paper right now for the time.
I think the time is a good thing to mention in this context of 10 petawatts that only exists for whatever 1 femtosecond. So 10 to the 15 watts in 10 to the minus 12, minus 15 seconds, I think. Anyway, I think that's a cool fact as well. Yeah.
doing math on a recording is always a risk.
Memorizing metric prefixes is always a risk.
Yeah, you're way more likely to mess it up when you're under pressure.
True.
Well, there was this I was talking to someone on the fiber optics, and when they send signal. I feel like this is almost the opposite, or what they're trying to avoid. Because I think when you send a signal or in the fiber optics, and if you have a constant frequency, because there's some impurities and such, it would stack up at some point in midway during the transmission and burn the fiber optics. And what they had to do is that crawl the frequency, so like modulate the frequency up and down to avoid that. Like it's like when we talk, I think we talked about congestion before, right? Like traffic jam. It's like a traffic jam, the ghost jam in fiber optics. And essentially what they had is kind of this focusing event, but you can avoid by changing the frequency and walk it. So in this case, it's almost the opposite way. They wanted to control it, so it amplified the amplitude.
You are 100% on the money, because the exact analogy that the people in this paper use is a traffic jam, a traffic pileup. They say, imagine you have like a line of cars driving on a flat road, and then they encounter a hill that goes up. All those cars will bunch up as they reach the hill. And they say that's kind of what's happening with this plasma mirror, with the light, though. So you're right. It's kind of the opposite of what you said.
So just reading the paper, they're taking picosecond pulses and then compressing them to a few femtoseconds that can get to something like 7.5 is it exawatts or some very large number. And the one highlight of this is the efficiency, because as Pheely said, components will burn out if you try and do this with using the classical methods, if you're trying to use fiber optics. And there's a whole study on laser ablation, which is the essentially removal of material using lasers. And so in this case, by using a plasma, you don't have to worry about any materials burning or frying or becoming optically opaque, because it's a plasma. It's already going to be quite hot, and the efficiency can exceed 99%, whereas there's a lot of power loss, especially in terms of heat and other reflections or refractions within the materials that can cause power loss. So this is a very efficient and a lot more powerful, because you can pump in a lot more power to begin with.
Yeah, and it sounds very clever, because I mean the way to chirp a pulse is you just put it through something with an index other than 1, and then different wavelengths will travel faster or slower than that. So the first way they did that, I think, which is a very long fiber, and this plasma just sounds like a very extreme change of index. And what's the volume of it? I guess I'm curious how. Yeah, if anyone knows.
About 10 centimeters, they said.
I mean, that's great. I think it was kilometers of fiber they had to use in the first case, but now they can do the same thing, or better than the same thing with the centimeters of plasma.
I think Donna Strickland had like a huge coil of fiber, right?
Yeah.
But that's not too bad, right? But the challenge for the plasma, how do you control to have the exact gradient of density of plasma?
Yeah, that's definitely a question.
It's a simulation, right? So they can just it's easy to program a change in density, or but it's really difficult to control plasma. And
I think they might be able to control it enough that they can get like an increase in power, but if you want the maximum increase you can get, that's probably hard to control, because you need probably a really specific density gradient.
And you have to probably study a bunch of other things, because maybe is it behaving like a fluid? Is there turbulence in the plasma? How you deal with that stuff? I think the fusion technology research had to deal a lot with plasma physics, which might help solve some of the problems that might arise when they try to make things practical. Right? Well, so I think that's a good place to move on and go to our main topic today. Unless anyone have lasting comment.
I did have one more interesting comment, because I happened to see Donna Strickland a few years ago at Photonics West when she was doing her sort of world tour after winning the Nobel Prize, and she was talking about sort of where these high energy pulses are going to go. And this is the question you guys will like, but she talked about getting, in terms of these peak powers in these short pulses, and you gave a lot of energy comparisons for it. In her talk, she gave the comparison of that we're eventually approaching the, I don't know what to call it, the binding energy of vacuum, and that we're getting to the point where lasers can, I don't know, rip apart vacuum. Maybe you guys can answer that better. I thought that was really cool.
I know a good amount about that. It's this thing called the well, I think what she's talking about is the Schwinger effect. So there's this thing where if you have a very large enough electromagnetic field, you can just spontaneously produce massive or massless particles. Like you could like produce electrons from the vacuum. You just fire this laser with really high intensity in the vacuum of space, and you can start making like whatever particles you want as long as you got the right energy scale.
You have the right energy, just creating pair production, just purely just from that enough energy, right?
Yeah, my research is about Hawking radiation, which is a form of pair production. So the Schwinger effect is really closely created. And it's one of these like fundamental results of quantum field theory that we can't test. So there's this thing called the Casimir effect, which is related, but the Casimir effect we can actually experimentally detect with like two metal parallel plates, and you can measure something. But the Schwinger effect is another one, which is like it'd be really nice if we can do an experiment that like does that and proves it, because it's one of these key results of quantum field theory which people just accept, but we haven't actually been able to verify it for a very long time. And if we do the experiment and something else happens, then we know, well, quantum field theory is struggling. But
cool.
All right. Looks like it's time to move on to Troy and his life and his works. All right, Troy. So Troy is actually one of the first people I met at Queen's. I was fortunate to move into the office where Fraser's group and I think Rob Noble's group were working, and I think there's a couple people from at the RMC who got assigned there allegedly. And yeah, I learned a bunch of things about lasers. I saw their little lab. It's interesting. All right, Troy, why don't you tell us a little bit about your research and maybe what you do?
Sure. Yeah, so you mentioned a bit at the beginning, sort of the broad topic I work in is laser welding and laser additive manufacturing. So basically using a laser to melt metal pieces together. And to sort of give background on that, on why that even exists and why it's important. I mean, everyone knows what welding is, and everyone can picture a person holding an arc torch, wearing a mask, sparks flying, and that's sort of everyone's picture of a welder. And you may be seeing them working on new apartment buildings, welding the steel struts together, or you can picture them on a factory floor building cars. And I mean, that's sort of everyone's basic understanding. And they've been around. Welding has been around for more than a century. In modern times, the amount of things we want welded keeps growing, and the amount of new things that need welding also, they pop up every year. But the amount of people getting into welding is sort of slow, and that's sort of a general trend of skilled trades not getting good high intake, and just a general labor crisis across the world. And that sort of pushed this need for automated welding techniques. And lasers were well suited for that because you can attach them to a robot, you can focus them down to very small areas, and they can very precisely apply heat to the pieces you want to melt. That is the sort of lead up to what I do, because automated welding is already happening. Lasers are being used to do it, in one part to replace and sort of try to ease the labor crisis and replace human workers on assembly lines. But also there's things like your phone probably has so many parts that were touched by lasers. The glass was probably cut by lasers. The body was probably, or the frame was probably welded together. The battery is probably welded shut. And those things, humans could have done that anyway. So there's applications that lasers are covering that couldn't be done before. But welding is complicated. Melting metal is not as simple as maybe people expect or like to believe. It can go wrong. And as it turns out, for any safety critical part like a car or anything going up in a plane, certifying those things and proving that they're safe and repeatable and not going to crack or fracture or break in the air or in your hand is difficult. So that's probably a lot to start, and I give more detail as you guys have questions. But that's sort of the field I find myself in.
Yeah, like welding. I remember, was it 2015, Patrick? The head welder for NASA, I forget her name.
Renee Horton.
Yes,
Renee Horton.
Yeah, she came. Yeah, Dr. H. She came to our university and gave a talk about like welding on NASA spaceships, and I just remember being like, "Oh, this is way more complicated than just some guy hanging from a rope, like with a welder, right?" And the amount of like they were like electron, I forget what kind of scans they were doing. They were doing like these crazy scans, like super zoomed in of the welds for like micro, or I guess nano cracks or whatever. Like I don't know the terminology, but I just remember it being way more complicated than I thought. And I guess that's kind of like the stuff you work on a little bit is, well, not NASA, but like
I wish.
There's way more to welding than the ordinary person might think.
Yeah, for sure.
Well, it is an entire craft, right? Like, I think I was watching something on welding patterns. Like, good welder has their own unique way of welding, so that everything is like nice and tight. There's no seal, no cracks, and it's a learned skill.
Mm-hmm.
But sometimes I wonder, like, well, aren't it supposed to be like the best way we can just program it to do? I even have problem with like welding in the first place, because let's say you work with wood, you don't weld wood, right? Like, but somehow metal welding is a method of choice. Troy, you know why welding is such a good thing? Why don't people manufacture things so let's say it clicks in like wood?
I mean, that so many amazing points you brought in there that lead directly into what I would normally use as my intro for my talks. So, I mean, okay, the first thing, the comparison to wood, I mean, how you join wood is with screws or nails, right? And that basically exists for metals in the form of riveting. And that riveting was, and still is used in some cases, but it was the predominant way to join metal sheets to make a large whole part, like, I mean, a ship, for example, back in World War II, were originally and still at that time made by riveting sheets together. And the story I like to tell, in World War II, American cargo ships were sinking faster than they could replace them, and they were all being made with rivets. So they made a new design that used welding already existed since the 1900s early on, but it wasn't sort of a large-scale technique yet. But they made a new ship design that decided they was going to use entirely welded hulls, because it was much faster than riveting. So that's one reason to use welding in the first place. So they trained a bunch of people to weld. They built these ships incredibly fast. I think a ship that would take half a year to build, it got down to like a month. And they built 3,000 ships to the same design in 4 years, which I think to this day is still the most of a single design of a ship ever built. Anyway, half of them had terrible cracks. I think a dozen actually just broke in half completely. And this was sort of called the largest welding experiment ever done. And they learned that when you take these ships that you build in port and then put them in the Atlantic, the temperature changes, the steel becomes brittle, and it'll crack, which would happen for a riveted hull anyway. But on riveted hulls, the sheets aren't fused together, so a crack can only propagate as far as its sheet, and it'll stop. When everything's welded together, the cracks can propagate forever. Anyway, a lot of lessons were learned. They found that untrained welders will leave cracks in welds, which then propagate. They learned a lot about fracture mechanics. And then, as you also mentioned, Pheely, humans are very easy to train and are very good at learning. So in the decades since World War II, when welding, first got introduced like that, welding has become a skilled trade. Humans are very good at it. A skilled welder can tell a weld is bad by the sound of it, and that's not just like a fisherman's tale. Like the melt as it's being scanned along will be oscillating at audible frequencies, so you really can hear when a weld is going good or bad. And they're so trained that, but just by their hand, they can feel when a weld is going well. And now there's robots coming into the workforce to sort of take over some of these jobs or do the same sort of job on a smaller scale for electronics or small devices. And they don't have the sensory motor abilities to hear or see what's going on and then immediately apply feedback and then change what they're doing or know that a weld was good or bad. And we have to do all of that for the robots, which is very time consuming. And they don't learn as fast as humans do. So that's a problem. And that's we're getting closer to what I do, is that these robots are really hard to train, and I'm trying to make it easier for them.
So it's not about the actual laser technology where, because I guess for welding, you have to use like continuous laser instead of short pulses that we discussed in intro topic.
Yeah, mostly, yeah.
Because you can melt metal by shooting, small pulses. Well, technically you probably can, but
take longer.
But yeah, it just takes longer rather than, you want to melt something, or like imagine what's the analogy here, right? Like people can probably make a oven gun where you just shoot a pulse of heat, try to cook your pie, but it's better to just put it in an oven that constantly turns on.
Yeah.
So I think is yeah. So in terms of the laser technology itself, it's already made, right?
Yeah, another great point. And this sort of coincides with, so there was a need to start automated welding, and the welder shortage has been going on for decades. So lasers weren't really suited, or there weren't lasers that were good at laser welding that were also affordable for a long time. Sort of gas lasers like CO2, continuous wave CO2 lasers were sort of popular for a while because they could give you like kilowatts of continuous wave power around like 10 microns wavelength. But around the early 2000s, I think, is when fiber lasers started to become available on the market that were affordable, that could give you kilowatts of power. And fiber lasers, you can
What do you mean by fiber laser?
So, okay, maybe I should go, how much background on lasers do you want? Basically, there's a gain medium, a cavity, and then you get light out of that. But yeah, I won't go into too much background, but basically in a fiber laser, your cavity is a fiber, and you usually dope that fiber with some sort of material that you can then pump electrically, and then that excites atoms, and then once you pump into the cavity, you'll get spontaneous emission combined with stimulated emission, and then stimulated emission within the cavity will give more stimulated emission within the cavity, and so on and so on. You get gain. And then, a fiber laser is a laser that's all
LED laser.
Fiber.
Right? It's like because there's like LED lasers, but that they're using like the semiconductor as a medium. But in this case, use the fiber.
Yeah.
When you say fiber, it's like a fiber crystal or like.
Yeah. So the materials will vary, but yeah, solid state lasers like LED lasers, they're also very similar, and they sort of all came around at the same time, and it's the same principle. The nice thing about fiber lasers is that the output is the end of the fiber, so it's like a light hose. You can just attach that to your robot very easily, and then it can weld. But yeah, these became available, and they were inexpensive, affordable, and good at what, and had stable outputs. Yeah, so it's not the pulse lasers you're talking about. It's not high peak power; it's high average power. But yeah, so those were the lasers that became available and sort of enabled laser welding to take off, and it sort of took off faster than we're understanding.
So where do you come in this scheme?
Right. So the traditional way to train welders, robot welders included, is you have them perform a weld, and you take that part, you cut it open, and then see what was done. What does the fusion zone look like? What is the microstructure of those grains? You can do pull tests, see how strong it is, stuff like that. That's time consuming. It also destroys your part. So in terms of quality assurance, you can't break open every weld you put into a car. You have to, there has to be some statistics applied to that. And historically, there hasn't been a lot of research done on, not what happened after the fact, not what it looked like after it's done and we cut it open, but what's actually happening while the laser's on, while it's melting, and what's going on there. So my research has been on optical techniques to probe what's going on while the laser's actually doing the melting.
So what kinds of processes are happening? Like it's clearly more than just metal melting metal and then forming one metallic object. So what kinds of things are going on that you're trying to measure? And I guess how exactly do you measure them? Because welding, from what I've experienced, is quite quick, and it's also very hot and bright and hard to look at.
Yes, all those things. So it's very bright. So your laser is kilowatts. So if you're trying to do any optical imaging of it, you have to contend with the kilowatt of laser light that is hitting and reflecting off of your metal. Metals are quite reflective. When I'm talking about fiber lasers, we're dealing with light at about 1 micron wavelength. And I think like steel, for example, reflects about 60% of that right off the bat. But with conduction, or I guess it's radiation, but it's still going to heat up enough that it's eventually going to melt. And for steel, that happens at around 1800 Kelvin. And that is going to conduct through the parts, melt everything around it, eventually reach some equilibrium as it conducts through the part, stuff like that. So that that you can weld in that mode where you just conduct, you just melt, and then you just keep scanning, and that's fine. That doesn't give very deep weld joints though. So if you crank up the intensity to the point where you reach the boiling temperature, so now that liquid steel that is still being hit by your laser now reaches boiling temperature. If you can picture when you're boiling water in your pot and you watch it start to boil, the vapor forms at the bottom of your pot, it expands and then floats to the top. If you could try to imagine that happening on the surface, if you were somehow heating the water on top, that vapor would expand right there at the point where the laser's hitting. So it's not going to bubble to the surface, it's already at the surface. Gravity is already, or it's not gravity, buoyancy is keeping it where it is. But it's going to expand in all directions, and it's going to push down on the melted metal that you have there. Now, once you push down, you've created a cavity. And now the laser beam can reflect. And when I said it reflects once and reflects 60% away, if you push your cavity down enough, you can now reflect twice. So now you absorb 40%, reflect it again, absorb 40% of that, and now you've gone, I guess, up to 60% absorption. And then now you're absorbing more, you're vaporizing more, you're pushing down more, your cavity's deeper, you can now reflect 3 times, and so on and so on. So there's this sort of runaway effect. Once you start vaporizing the metal, you get this cavity, your laser can reflect more times, you absorb more energy, which pushes the cavity deeper, and so on. So now in this area, you have a cavity. It's surrounded, its walls are made of molten steel near boiling temperature. Behind that is more molten steel, and eventually that goes away until you reach solid steel again. And that all takes place at the tiny spot of a laser beam, or laser beam spot size. So we're talking about hundreds of micrometers. It's usually moving, usually scanning it along somewhere. So there's movement there.
What's the time scale of that?
Time scale?
Pretty quick.
Pretty quick, yeah. I'd say that all could happen in the first 100, less than 100 microseconds during the laser on. I mean, that's slow to other time scales, but yeah, 100 microseconds, 100 micrometers, sort of length scale, 3000 Kelvin, light interacting, bouncing around. And now that cavity is open and it's sort of pushed metal, melted metal up into the sides to create a cavity, you have that vapor pressure pushing it out. But eventually you can't absorb any more. You can only absorb up to like 100%. Asymptotically, you'll approach that as you couple more and more light into that cavity. But the forces of gravity and surface tension that don't want that cavity to be there will keep growing exponentially. Actually, not exponentially. They'll keep growing anyway. I don't know if it's linear or exponential, maybe. Anyway, they'll grow. So at some point, you'll push enough metal out that the cavity wants to collapse. And now your shape is sort of changing dynamically. And as your shape changes, the amount of energy you're absorbing changes, and where it's being absorbed changes. So that's also changing your shape. And its metals are very opaque. It's hard to see in there. That vapor depression, that cavity that is formed, is impossible to image inside of because it's highly absorbing. And so the dynamics of that vapor depression, sort of sometimes called a keyhole, that leads to a lot of defects as well. So if that cavity collapses and you just keep scanning, you'll just have trapped vapor in your weld joint. It's called a void. That weakens the weld. As it's sort of sloshing and vibrating around, it can spit out metal. So it can spatter molten metal onto the areas next to your joint. And if you're working on a sensitive piece of equipment like a battery or a medical device, you don't want that. But also if the cavity collapses entirely, now you're not welding as deep as you want it to. So it's kind of a mess. To leave anything out.
When we see people weld, it's not like they're dragging the thing along. It's like almost like a pulse, right? It's really when you look at a welding pattern, sometimes it looks like a bunch of circles.
Yeah, so that could be a spot weld, and all of what I just said there still happens in a short spot weld. It depends on the time scale. I mean, I don't know exactly what application you would have seen there, but even on the scale of like milliseconds, like 1 millisecond weld, all of that can happen. Depends
So
on the
with
spot
all those
size,
challenges, do you image during the welding, or you just or like is it by through some clever filtering out light you don't want? Like how do you actually get to know what's going on while you're welding?
Yeah, so I use two techniques. One that was, I didn't invent either of them, but one was invented by a former grad student of my research group. It's called inline coherent imaging. It's basically a Michelson interferometer where you have a light source coupled into it, and then you have two arms, your reference mirror. So one arm just goes to a fixed reference mirror. The other arm gets fiber coupled coaxially, so in line with, that's where the inline comes from, with the laser that you are welding with. And that basically means that shiny piece of metal that you're welding becomes one of the mirrors of your interferometer. And then when the light reflects off that reference mirror and reflects off of that welding that you're doing, they'll be recombined into the interferometer and get sent to a detector, and you can interferometrically measure that path length difference and infer how deep you're welding. And that's especially useful for what I mentioned, those cavities that open up. You can even measure to the bottom of those. It's sensitive enough to measure how deep those cavities go in real time. Another important feature of that technique is that it can measure hundreds of kilohertz imaging rate. So you can sort of capture events on the 5 microsecond time scale.
Oh, well, I never thought Michelson interferometer can be used this way. This is pretty interesting.
They can be used for so many things, can't they? Like a lot of the time, if you have some problem at least in like ultra cold physics, you just slap a Michelson interferometer down and see like, is there any way we can jerry rig this into our setup to tell us something? How does
Well, this is also easier too because you already know one of the lights, right? The interfering light is already your source, the one you work with. So you just need another one to interfere with it and try to capture it.
Yes. So the source is being split between two arms.
Yeah.
The one that gets combined with the welding laser, it does not interact with the welding laser. It's a different wavelength entirely. It's the known path length of the reference arm compared to the unknown path length of the welding arm. We're only measuring the difference between those two, but we know the reference arm is fixed. So then we're getting the distance. And the interference only happens once they both recombine. So we're I don't mean to correct you in case you understood, but we're interfering the source light in both cases. They just came from different arms. Yeah.
So that tells you how deep it goes. But I can imagine that there's all these extra things happening that might affect the path length, that might mess with your measurement, right?
Yep. So like I mentioned,
so I guess it's like a whole science to filter those out somehow.
Yeah. And some things you can't entirely filter out, but like I said, the cavity can collapse sometimes, and it can spit out molten blobs of molten metal. And if those get in the way of your beam, your imaging beam, you're not going to probe through that. So you'll get a false shallow measurement because the cavity either partially collapsed or there's some spatter in the way.
You got to be careful when you're doing it.
Yeah. I mean, you can't really be careful. You kind of just let it rip and then just process what you get. I mean, you can't.
I mean, that's research.
Yeah. I mean, we're not at this stage, at least in my way, I'm not trying to control the process. I'm just trying to image it and show people what's there and let the modelers deal with how to understand it and how to tailor the process. And that's sort of my spirit of research. I like to just let it do its thing and just observe it. But
I think this is a good point to pivot into your life a little bit.
Sure.
Because, what really got you into this type of laser research or even more like manufacturing research? Because as I understand, you have a undergraduate degree in engineering and you kind of pivot into the physics. So, can you tell us your story on that?
Yeah. So my undergrad was in engineering physics. And so engineering at Queen's is a general first year where you don't declare your engineering type yet. And you sort of do that, I think, halfway through second semester. There's like seminars and events to try to woo people into certain categories, whatever, disciplines. And I mean, the honest answer is, I think I was between maybe electrical engineering or engineering physics, or maybe mechanical engineering. And I went to the event nights for that. And in mechanical and electrical, they were sort of showing you all the cool courses they work on and stuff like that. And like, oh, we're the most popular one. You should join us. And the Eng Phys night was basically, this is the hardest engineering discipline. You should not take this discipline if you weren't good at physics. This is not for everyone. And I was like, if you're telling me it's the hardest one, I have to do the hardest one. Like it was a pride thing, which is not a good reason to go into physics. But I have to admit that once someone told me like, oh, you shouldn't do this unless you're really ready or you're really sure, I was like, I'm definitely going to engineering physics now.
That's a respectable reason.
Yeah, thank you.
The pride.
Yeah. Liam has a similar story, right?
Yeah.
He said like, this thing is like he couldn't solve, so he was just like.
I know that all these physicists always say like the learning, like getting to the end result is the beautiful part, but I don't know, man. I just get really frustrated when there's like a problem and I want an answer and there's no answer and I can't figure it out. I just have to like pound away at it until I have an answer.
Yeah.
I like having answers.
Yeah.
Getting there is very fun, but I like the result as well.
So that's got you into engineering physics. Can you tell for the audience just briefly, like what makes engineering physics different from engineering and physics?
Oh, good question. I guess at an organizational level, it's an undergrad in basically half mechanical engineering courses and half pure physics courses. And so the physics courses I was taking, we were taking them alongside the physics majors. And then the engineering courses, I was taking them alongside all the mechanical engineers. And you can pick
So
which.
you learn like quantum mechanics and
Yeah,
stuff. Or...
Yeah. Starting in second year, we start with whatever relativity and quanta, and then you get into quantum mechanics in third year. Yeah, same timeline you guys probably
which
went
is
through.
not usually engineering courses.
No. And then there's also difficult math courses in third year as well. And second year, you also take the math courses alongside the physics students. That's also a difference. But you also get the sort of group project aspect of engineering courses, which are, struggles, but I think good for personal and professional development.
They're character development.
Yeah.
They build character.
That's the one thing they do.
Engineers, we have to work. You have to work in a team, right? So I think that's kind of helpful. And also, so then you move into PhD, but is it in engineering physics?
It is in engineering physics. Yeah. So throughout the undergrad, I mean, it was a struggle, which maybe shows that I maybe made the wrong decision. And I got through it though, and sort of, I mean, it wasn't as that bad, but it was sort of, courses were difficult. It was a struggle to really grasp things. It took a lot of studying, as it always does.
So the reputation was warranted.
Yes.
When they said it was hard, right. It was hard.
And then when I got to fourth year, I took a course in laser optics taught by my lecture supervisor, James Fraser. And that was just a course that I just got. It's just like, oh, this is how laser works. This is the cavity, light, emission, gain, whatever. I didn't have to study too hard for that course. And that just sort of told me, I think maybe I just have a knack for optics. And then I pestered him over the semester to take me on as a grad student, and he agreed. And then 6 years went by, and now I'm here. So, I guess the main question, how to get into physics or optics or into grad school, it was just a fourth year course that I just really enjoyed and it just came easier to me than all the math and stuff, and other more pure physics topics. So, yeah.
Well, we do things that we're good at, right? I think, and that as one thing that a lot of people found it out in high school when they were very young. Some people found out when they're 40 years old, and it is a different time of more like a metamorphosis for everyone, right? You found this caterpillar, you found a way to work with your life, and here you go. This is your career. So I want to delve deeper into the walk into the memory lane a little bit. So actually, what got you into like engineering in the first place? Was it started when you were really young, or was it more like interest you had, like in, let's say, in middle school or high school? Was the science always your thing, or science and math growing up? Was it the thing for you, or was it more like a later on thing?
Yeah, I'd say it was pretty early on. I was good at school. I liked math. I liked science. So I think from a young age, I was thinking about, I'll be a scientist someday or a doctor someday, as any second grader might think. But when it came to choosing what to do for university, I felt like I could have picked anything. But when it came down to physics or engineering or a science, it was sort of as an 18-year-old, I was making what I thought was a practical decision that engineering was a more financially prudent decision to study. And whether that's true in reality, I don't know, but that was where my mind was at as an 18-year-old. And there were probably people telling me that in my family or around me. And that was sort of I don't know, you guys have had similar feelings then or even now that's what people say, comparing physics or pure science to engineering. But
yeah, I think it's a safer bet I feel like if you do really well in physics, you're fine, or even like any other science. If you go into biology, you go into chemistry. If you're like top of your game, you're fine.
Yeah.
But if you go in engineering and you're just okay, you're still probably fine.
Yeah.
You'll still get a good job. You'll still, help society. You'll still make a difference and get paid and have a job, even if you're not like the top tier of your class or whatever.
Yeah.
Well, academic research is more unclear, right? Engineering, like people build stuff or create stuff. There's a product that people make. But in academia, the product is like the paper, this abstract concepts. It's hard to quantify or even put value on what idea or theories are more valuable than the other. But sometimes clearly, well, sometimes when you build a bigger bridge, maybe connecting larger people, it's just more obvious to what value it contributes to society, and it's more immediate too in a lot of engineering fields. And actually, I'm gonna pivot into the future a bit. So now that you're completing your hopefully final PhD, or maybe
done.
more PhDs.
Yeah. Congratulations,
Yeah,
by
I'm
the
done.
way.
Thank you.
Dr. Troy Allen. Congratulations.
Yes. Oh, that's
Oh,
good.
we can put that on our episode. We can say with Dr. Troy Allen now.
People think
You're
I'm
the
a
first.
professor.
You're the first doctor we have on the podcast. I think
Really?
actually. Yeah, I think
Yeah.
so.
Oh, wow. It's a great honor.
Yeah. So we always ask this, or actually I always ask this to all our guests, and it's about hopes and dreams. And I think you're the one that I think the furthest along the line. So what I mean by that is like, so who do you see yourself being? I'm not talking about like 10 years, 5 years, no timeline. It's like, would you like to be, let's say, a professional engineer working somewhere in laser technology, or do you want to move into more academically inclined field? Who do you see yourself being?
Yeah. So when I got into grad school and I was studying optics and those imaging techniques, interferometry, whatever, I happened to be looking at laser welding. But what I really thought was valuable was the optics experience and the imaging experience, because that is so applicable to anything. And it's also spectroscopy involved with the interferometer, but I didn't get into that. But anyway, and what I always wanted to do was to take those imaging principles, that training, and get into space exploration, space imaging, something like that. And I'm very lucky that I've landed at a company that they do a very broad application space of spectroscopy that includes some space clients. So in some ways, I'm getting there. But I just love optics. I love how versatile it is, and I just really hope I can take it and pivot into just some really cool stuff in the future. Looking, I don't know, on a rover or something would be my dream, to be the guy who built the camera or built the imaging system for a rover on Mars. I don't know.
I've heard
It's very transferable skills.
Yeah.
I've heard some of these rovers have lasers that they'll shoot at the rocks, and then they'll use spectroscopy to determine like what's in them. So like there's like immediate applications of lasers in space.
Yeah. So for a while, I mean, I'll be working where I am, where I can get work. Not that sounds like I'm not in a good place. I love where I work already, but I feel like at some point after a couple of years, I'll be in a position where I can choose where I work, hopefully, and then I'll look for that. But
Well, I think this what's it called? The application is very wide for optics because like the information we have from most things in the world are from light, right? Like that's at least in my opinion, is especially more in space, because it's really hard to get somewhere, and using light as a medium or as a tool is extremely important. And that's why I think like your group is very versatile in terms of industry. And also I kind of want to comment on this too. I feel like there's this what's a set of companies or industrial technology that's not accessible to, let's say, non-graduate students, or let's say you have like a undergrad. Is there more like a place that usually hire a lot more PhD or master students who work on like advanced tech, or is it more like is there a special place, let's say, for PhD graduates that usually take PhDs?
Like geographically?
No. I mean, like,
Types of
do they
companies?
exist?
Uh,
Yeah.
Probably. I mean, I definitely looked for them when I was looking for jobs. And I'd say my job search story isn't that helpful, or well, maybe it is, but yeah, I was trying to look for places that were hiring PhDs, but not undergrad engineers because, I'm overqualified for that. But like, there's very few job postings that say PhD required in them. So maybe that's where your question's coming from. But I ended up getting a job from a friend that interviewed somewhere because she bought something from this company in the past. They remembered her, brought her in for an interview. She politely told them that she wasn't close to finishing, but she knew that I was, recommended me. I interviewed and then I got it. So I didn't even know this company was hiring. I didn't even know they existed. But it's who you know, which sounds dismissive, but it's literally your network. A friend of mine who is a former grad student in our group, we kept in touch, and that's just how it goes. So yeah, PhD jobs are probably more rare, and you might have to hear of them from other people who are already working with a PhD or still in grad school. But also, so my advice for that is, what kind of companies do you buy your tools from? Because if they service PhD level researchers, they probably have PhDs there too. So that's one option, is to work at the people who supplied you over the years. But
Well, one thing I find about PhD is that you learn to be an expert in a very specific thing, then you learn a lot of skills along the way. Mostly, at least for me, how to do research, I do like computational physics and such. But what do you think, like a doctorate, like offer to industry? Like, or what's the difference? Let's say if I gonna hire undergrad engineer, trained in for 4 years,
yeah,
then a doctoral student.
yeah, I had a conversation about this with someone at work today, actually. And I mean, it's a very simple way of describing it, but like, he was lamenting that his time of being a doer and a thinker are done because now he's a manager and he's just a decider. And he said that I'm lucky because I get to be, a doer and a thinker still. And he contrasted that to an undergrad. You hire a fresh engineer, and they're mainly just doers. You'll give them tasks to do, and they'll do them over many years and gain experience. And eventually, they have 10 years of experience of doing small projects along the way. The advantage you have as a PhD student, especially if you did the same project during your master's, is that you spent 6 years thinking about one problem or world building, like one specific skill. So you have that big picture idea and the ability to think about a project over that long time scale. And you were constantly the doer and the thinker and the decider. In some cases, you were all those things the entire time. You jump into a company and then they know that you already have those skills and they can trust you to work independently. They can hand you a problem and trust you to overthink it and come up with 10 possible solutions for them. So I think that is something I found has helped me so far in the 3 months I've been working. On top of that, you probably did presentations, you probably did the conferences, you probably wrote papers. It's also really valuable, and you don't get that in undergrad. So I'd say that.
Right. I think that's a wonderful way to look at the doctoral degree too, right? It's not just, like, oh, we get this academic thing only. We learn a lot of skills along the way in terms of research. All right. I think that was great, Troy. Yeah, thank you. I think we're gonna kind of naturally move on.
Sure.
Hopefully. So yeah, so we have done quite like an hour or so now. So, well, I'll let Patrick tell everybody about how to contact us and such, where to find us, and hopefully a little story.
Yeah. So if you are interested in reaching out to us, there are many different ways that you can use. We are on Instagram. You can find us at the Hyperthesis. You can also find us through our email address. We are hyperthesispodcast@gmail.com. You can send us an email, a DM over Instagram, however you would like to, especially if you would like to be a guest on the show. We're always looking for experts in your area of science, and it doesn't matter the science. We've had guests studying astronomy or simulating oceans, or today we have Dr. just to highlight that, Dr. Troy, who is being very gracious and coming on the show today to talk to us about how he's able to research with lasers and welding and using very interesting techniques. So if you would like to be a guest on the show, reach out to us through Instagram or email. And Troy, if people would like to reach out to you, do you have a preferred method?
They can go through you because you can reach me, but I'm not on social media.
Sounds good. So if you have questions for Troy, just send us an email or a direct message, and we'll make sure that your question or comment gets passed on, provided it's a nice comment. You can also find us on YouTube. We are at the Hyperthesis Podcast. You can just search that in YouTube and we will appear. And you can also find us wherever you find your podcasts, whether it be Spotify, Google Podcast, Apple Podcast, wherever you can find us. You can listen to us, you can share, and feel free to subscribe, to like, and leave a review or rating on our videos.
All right, so today's story is also coming from Patrick. And so he's going to be telling us about the story of the Theodore Maiman, and the laser. I'm not sure how to pronounce that.
That's okay. So I'll make this story quite quick, but we've been talking this whole episode about lasers and about some other things as well, including welding. But I figured it might be cool to touch on the first laser and the man behind it. So many of us have used lasers in everyday life, whether it be entertaining cats to using them for research or welding or industry. They're everywhere in our life, but they have very modest and somewhat controversial origins. Now, the first laser, as Pheely mentioned, was made by Theodore Maiman in 1960, and he was an experimental physicist who worked at the Hughes Research Lab. We'll get into that in just a minute. But first, I just want to tell you a little bit about Theodore Maiman. So his story begins in Los Angeles, where he was born to his father, Abraham Abe Maiman, an electrical engineer and inventor, and his mother, Rose Abramson, who was also an inventor. These two ignited young Theodore's curiosity by involving him with experiments in their home electronics laboratory. And that's quite the influence to have, where you have an electrical engineer as a father and an inventor as a mother. So lots of good, positive, scientific influences there. Now, at a young age, Maiman's family moved to Denver, Colorado, and that's where Maiman continued to assist his father in their home experiments. Now, Maiman was a hyperactive kid who said himself that he would be a perfect candidate for Ritalin, and he most likely had ADHD based on descriptions of himself. However, it wasn't very commonly diagnosed at that time. Now, in his teens, he found ways to channel that energy and earn money by repairing electrical appliances and radios. And even by the age of 17, he was already employed as a junior engineer with the National Union Radio Company. Skipping forward a little bit, he served with the United States Navy at the end of World War II, and afterwards he pursued his higher education. He earned a Bachelor of Science in Engineering Physics, sounds familiar, from the University of Colorado, Boulder. But that was just the beginning for Maiman, because he ventured into graduate studies at Stanford University, earning a Master of Science in Electrical Engineering and a PhD in Physics in 1955. Now, Maiman's doctoral thesis was conducted under the guidance of physicist Willis Lamb, and it focused on experimental physics. His work involved intricate microwave optical measurements of fine structural splittings in excited helium atoms. There's not nearly enough time to get into that, but not only did he do this experimental work, he also delved into theoretical aspects, and he designed laboratory instrumentation that was crucial for these experiments to happen. Now, it was during these years that Maiman's experiments began to lay the groundwork for what would become the laser. His exploration of the helium atoms and fine structural splittings became instrumental to his breakthrough that would eventually produce a laser. Now, fast forwarding to around the year 1960, Maiman was able to use a ruby crystal that, again, as we mentioned in the episode, through stimulated emission and by pumping energy into it, was actually able to laze, which is to produce coherent light. And so this ruby crystal was coated in a silver, very reflective material, and this was the first laser. It's actually really neat to see a picture of it because it looks super futuristic, even though lasers nowadays, as Liam held up earlier, are just like, can be little black boxes and handheld, whereas this was a little bit different. Now, Maiman's findings, he wanted to publish right away and did so in physical review letters, and the response was actually unexpected. It was a rejection. Now, this rejection left Maiman undeterred and prompted him to turn to a slightly better publication, which is known as Nature, which we were discussing earlier in the episode. Now, this paper was eventually published on August 6th in 1960. Now, it's interesting that such a monumental item was rejected, and there's a lot of speculation about why it was rejected, but there was apparently an overwhelming number of papers on masers, which are the longer wavelength predecessor of lasers. So lasers use visible light or close to visible light, whereas masers use microwaves. So there's a lot of controversy around that, and I mean, in terms of the physical review letters, that's quite the loss for them. But in 1960, the laser was invented, and it's now just being used everywhere by pretty much everyone. You try and find me a person who has never used a laser before in any way, and I will be very impressed. Now, this is quite an important discovery, and Maiman's discovery has been listed as the top 20 or the top 5 and has made many different lists for the best invention in the world. And so, really, his mark has left a permanent imprint in the human race and all the technology that we use, from welding to playing with cats. His legacy truly continues to live on in any light that you see that's a little bit coherent.
All right, thank you, Patrick, for the amazing story of the first laser. And thank you, Troy, for coming. And we will leave everyone here. I'll see you guys next week. Take care.
Bye, everyone.
Bye.
See ya.